Bismillahirrahmanirrahim. Assalamu alaikum viewers. Welcome to my channel, and in today's video we are going to discuss the last topic of the relative series, that is how to convert the non-exact ordinary differential equation into exact form. So in this video we are going to discuss the last rule, the first three rules, and the video relating how to solve exact differential equations of first order are already been have been discussed. You can see the relative links in the description box for more exhaustive overview. Okay, so if I say that I'm having a certain differential equation that apparently looks like a total differential equation or exact differential equation of this type, but once when I try to check whether it is really a total differential equation or not, I try to find out the partial derivative of this function with respect to y and the partial derivative of this function with respect to x, and I find out that they are not equal, then I will conclude that this equation, which apparently I must say looks like this, is actually not total differential equation. So I have to convert it into exact form or in total form. For that purpose, if I feel that for the first three rules are not going to help us out, then we'll definitely move towards the rule 4. So the major key, or the major sign that makes us to decide that we should use here rule 4 is that this equation should look something like this. Over here you can see. Okay, so once when we see the example, this thing will further gets clear in our minds. So just think in a way that if I am able to take out y common from this function and x common from this function, then this condition is going to be satisfied. Then in that case we are going to apply rule 4, otherwise not. Okay, so what is our rule 4? In rule 4, what we do, we apply this step, and if this thing is not equals to 0, then the reciprocal of this expression is going to behave as the integrating factor, which is this. Okay, and this integrating factor we are going to multiply with this equation entirely, then it is going to be converted into exact form that we are further going to confirm with the help of this step later on. Okay, and then we are going to apply the same procedure or the same strategy of obtaining solution of the exact differential equation. Now let's see an example here. Over here you can see the example. Okay, so this is the beautiful example here. We can see that this is our m, this is our n. Okay, and I just forgot to write my dy here, so let me just write it down. This is our dy. Okay, so this is going to behave as our m like this, and this is going to behave as our nxy like this. So this differential equation, or the left hand side of this equation, clearly reveals that I am able to take out y common from this part and x common from this part quite easily. I've just taken it out already here, you can see. Okay, so you can see that this function is totally different from this function, right? This one is totally different from this one. That's why we just represent this thing as fxy and this thing as gxy over here. I hope now that the theme is cleared in your minds. Okay, now what we do, we are going to use here this strategy, try to check out is it really giving the result non-zero or not. So let's now try to just multiply. This is our m. Okay, and subtraction with y times this n, like this. And let's see the step. It's going to give me 3xy plus 4x squared y squared minus 2xy minus 3x squared y squared. So what we are having now here, we are now having here xy plus x squared y squared, and definitely they're not vanished. It means this stuff is not equals to 0. Okay, now once this thing is not equals to 0, this thing is non-zero now, we are going to take the reciprocal of this stuff, which is this, going to behave with an integrating factor. Okay, so our IF, or integrating factor, is the reciprocal of this thing. I can take out my xy common from these two terms. Let's take it out. So inside is this thing is left. Okay, so this is our beautiful mu xy. Okay, the notation that we use for integrating factor. Now we are going to multiply this integrating factor to this entire ODE. Let's see what we get. So I'm going to take this this format while multiplying my integrating factor. Okay, so so you can see here this x and this x, this y and this x and this x gets cancelled. So the thing so left is this. Okay. All right, now this is now another differential equation that looks like total differential equation. We have to confirm now, is it really total or not? Whether it has really been converted into a total differential equation or not. So for that purpose, what we do, we are going to find out the partial derivative of this function m with respect to y and this function n with respect to x. Let's see how those two answers are equal or not. So we're going to apply the conventional derivative rule. So of u by v order. Okay, so v derivative u is v times derivative of u. So I'm derivating this thing with respect to y, so here x is going to behave as a constant. So what is going to left here is 4x minus this thing minus this thing into derivative of this stuff. So it's going to give me x squared upon v squared, which is this. Okay, so we are going to simplify this thing now. When we simplify, we are going to get our answer. So I'm not doing that step, I'm directly writing thing. I think I should write down. Okay, so here you can see that I did a little mistake. I'm sorry, it's x cubed pi. Okay, so this thing and this thing gets cancelled. What is left is x squared upon x squared times 1 plus y xy whole squared. This thing get cancelled, and I'm having the partial derivative of m with respect to y is this. Okay, now I'm going to take out the partial derivative of this n with respect to x. I should get the same answer. Okay, so let me make a nice demarcation. Okay, so now I'm going to take the derivative of n with respect to x. So it is 3xy upon y times 1 plus xy. The same process I'm going to repeat of derivative of u by v format, and when I just solve this thing, I'm going to get the same answer. So here you go. So that's how it looks like when I take v derivative of u minus u derivative of v upon v square. It gives me this type, and you see that this thing and this thing gets cancelled. What I'm having here is y squared in the numerator and y squared times 1 plus xy whole square in the denominator. This gets cancelled, and you can see we are having the same result over here. So it means that these two answers, as they are equal, or we can say that f of xy is equal to fyx, so it means this is an exact differential equation. Now we are going to get the solution of this exact first order ordinary differential equation. So what we do, this is our fx. So this is our m, and this is the partial derivative of f with respect to x. So the same process. So this is our m, which is this. Okay. I'm going to represent my solution function as small f. Okay. So it was this. What I'm going to do, I have to find out the integration. I have to perform the integration here in order to get f of x. So let's see what we get. So once when we perform the integration with respect to x, okay, so we can break it. We can break it in this way. So as we are integrating with respect to x, it means our y is going to behave with a constant here. Okay. So once when we try to integrate by splitting this integrand in this way, it gets quite time consuming. So if we just try to transform this integrand in this form, it's gonna give me the same result, of course. It's gonna give me the same result, this thing back. Okay, so now my integrating sign is quite weird. I hope you can cooperate. So I'm having this thing here. So you can notice that as we are integrating the integrand with respect to x, so over here y is going to behave with a constant. All right, so over here if we just try to use u substitution, so it is going to give me, like, if I just let 1 plus xy equals to u, and I try to differentiate this thing, and I'm going to get d upon dx times this thing equals to du upon dx. Okay, I'm going to get y here times dx equals to du. Okay, so I'm getting y times dx equals to du. All right, so it is going to give me it's going to give me 1 upon u du. So the answer that I'm going to get here is this. Okay, plus some constant. Over here I'm going to use constant as this thing, some function with respect to y. Okay, because y is going to behave with constant here. Now I'm going to restore the u, and u was 1 plus xy. So my function fxy is this. okay, plus h of y, and I'm going to name this equation as equation number 1, and I could just close it in a nice box. And now the second objective of mine is to get the value of hy. Okay, so what I'm going to do, if I differentiate this function with respect to y, then I'm going to get this thing 0. Alright, this thing will become 0 because this x is going to behave with a constant here, so derivative of constant is 0. This whole thing will become 0, and the ln of this thing is 1 plus xy times 1 plus xy, and then once when I apply my chain rule here on this thing, I should use partial derivative notation. I should use this notation plus the derivative of this function. Okay, so the answer that I'm going to get is x upon 1 plus xy plus h prime y, and you can see that the derivative, partial derivative of f with respect to y was this function. Yeah, that was your n. So I'm going to write this value or this function at this place. Okay, I'm going to write this thing over here, y times 1 plus xy equals to x upon 1 plus xy plus h prime y. Okay, these two things will get cancelled, of course. So what I'm going to get here is h prime y is equals to 2 plus 3xy upon, well, I must say that I cannot cancel these two factors because this factor is not underneath or not in the denominator of h prime y, so I cannot cancel it out. So how about if I just shift this whole thing over here and perform the LCM work? So that's much prudent step. Okay, so once when I apply my LCM step, I'm going to get 3xy minus xy upon y times 1 plus xy. Once when I simplify, I'm going to get 2 plus 2xy upon y 1 plus xy. So you can see once when I take my 2 common here, my h prime y is going to behave this thing upon y times 1 plus xy. So these two things are now mathematically permissible. It is to cancel them out, and we just did that. So h prime y is equals to 2 upon y. Alright, this is it. Now we have to obtain actually h of y. So what we do, we are going to integrate h prime y, and we are going to get the value of hy that we are going to substitute here, and we will get our function back. So my page is exhausted. Now let me manage a new page to continue the work. That's what we have just obtained, and let us now integrate this function with respect to y. Now we are going to get h of y back plus some constant. Okay, we are going to substitute this h of y value exactly over here. Okay, and this is gonna give us the function which is the solution of this differential equation, this one. So fxy is equals to 3 ln x plus ln 1 plus xy plus h of y, which is this, plus some constant. Okay, so we can reduce this stuff in this way. You can use here the basic laws of the logarithms like this, and this is our constant. So constant could be the logarithm of some another constant, right? So, and you know that all the positive logarithms are basically the logarithm of the product of these values. We can express our answer like this. x cubed, let me use a big bracket here, x cubed y squared c prime 1 plus xy. Okay, so this can behave as our solution f of x for this differential equation, which was basically non-exact. We converted into exact form by using the rule 4, and then we performed this entire beautiful strategy. Okay, and finally we got the solution. Okay, so once when this f is going to be substituted here, it's going to satisfy this first order ODE. Okay, so I hope now if you just perform a set of questions, and if you just perform a bunch of questions here relating to this concept or this topic, you will definitely find your grip more strengthened. Okay, so just practice maths as much as you can in order to gain more expertise. All right, if you find this video helpful, please subscribe my channel, hit on the like, and share this video as much as you can with your friends and other learners, and don't forget to put your comments in the box below. Take good care of yourself. Allah Hafiz.